Shalom for the invitation to this seminar. It's always a pleasure to be in Vienna. Sorry. Okay. Okay, so this is the closest I will come to Vienna in the near future, because Israelis with an Israeli passport cannot come to Vienna without a special invitation. Okay, so this is joint work with Mark. So what is the model that I'm going to discuss? The model that I'm going to discuss is maximization of a difference of two convex functions. So it's f of ax minus gx. A is a matrix, n times b matrix. F is proper closed and strongly convex. We'll see later on why it is important to say that it's strongly convex. And G is a proper closed convex. And the special property that G has is that it has a compact domain. Also, I assume that the domain of G is contained in the domain of H. H is the composition of F with the linear transformation AX. So the domain of this guy is included in the domain of this expression. Of course, we can have situations where we have infinity minus infinity. And in this case, the convention will be that infinity minus infinity is minus infinity. So what are the main goals of this talk? First of all, we'll find improved optimality conditions. Of course, I will first have to explain what is optimality conditions which are not improved, but we'll see later on. And develop some randomized dual-based decomposition methods for this problem. Of course, this problem is non-convex because it's when you take two convex functions and you look at the subtraction, then of course it's not convex. So I will also have to explain what is dual-based method for a non-convex problem. But before that, I want to give you some motivation for why I'm looking at this model of f of ax minus gx.
So there is a question, Amir, max or mean? I mean, yeah, probably the question is, there is a question, max or mean? So probably the
no, it's max. Here it's max.
And then why max is, yeah.
Because of this, okay. The question is, of course, completely legitimate. Of course, even if you look at the max or mean, then of course it's in either case it's a difference of convex functions. But the real reason is the three examples that I'm going to show now, and they are all naturally max problems. So this is the reason why I'm looking at the max problem. So I will look at three PCA prototype problems. These are just like three examples that will accompany us throughout the lecture. Let's start with just the principal component analysis, but the standard PCA that we all know. And in case that we don't know, then this is just a small reminder. If we have n points in a d-dimensional space, we want to find the first PC is to find the normalized vector x, for which the projected data, the data that is projected on the line spanned by x, and it is given by these scalars, I transpose x, has minimum variance. So usually what we do in PCA is that we assume that the data is centralized, meaning that the sum of AI is equal. So in this case, of course, the variance is the sum of the squares, the sample variance. So actually what we need to solve here is the maximization of this sum of squares subject to the fact that the vector should be normalized. We will always denote A to be the data matrix, meaning that we take the data A1 to AN, put it as rows of this matrix A. So the rows of the matrix correspond to samples and the columns correspond to features, like we always do in data science. And then the problem, of course, becomes in this formulation, maximization of the L2 squared norm of AX. And over the L2 unit ball, as you can see, I replaced the sphere constraint, the equality constraint, with an inequality. And of course, it's okay to do that because we know that the maximization of a convex function is equivalent to the maximization over the convex hull of the feasible set. So And of course, this fits the model of f of ax minus g of x. When we take f to be half L2 squared norm. Okay, I know that I don't have half here, but just imagine that there is a half in the PCA problem. It's also not that important. And G is the indicator of the L2 ball. So we can see here also that all the assumptions are met. So F and G, of course, are convex. F is also strongly convex. G has a compact domain. So this is the first example, very well known. A second example, which is also very well known, but of course, it's much more recent than standard PCA. Let's look at sparse PCA. There are a lot of papers about sparse PCA, and there are a lot of formulation. I will use the formulation of Despramont and the co-authors from 2005. That what I do is just I add the constraint that the L0 norm of X is less than or equal of S. And as you all know, of course, the L0 norm is just a number of non-zero elements in the vector. But the problem here, of course, is that it doesn't fit the model P because we do want to assume that the feasible set would be convex. So if I would write G to be the indicator of this intersection of the L2 unit ball and the L0 ball, then it doesn't fit because G is not convex. But again, exactly like I said before, it's equivalent to maximization over the convex hull of the intersection of the L2 and L0 balls. So yes, it does fit the model P with F equal to the half of L2 norm square. And again, at least I'm consistent. I forgot the half in the problem formulation. And G is the indicator of the convex hull of the intersection of the L2 ball and the L0 ball. And yes, if there are questions, you are most welcome to ask. The third model, the last model, the example, it's also a kind of a PCA formulation, but now I'm using the second interpretation of PCA. It's the interpretation that of Pearson from 1901. The end result, when you look at standard PCA, it's the same, but the whole idea is different. So let's say again that we have this point A1, A2 to AN. But now what I'm trying to find is a vector X, a normalized vector, for which the sum of square distances between the points and the line spanned by X is minimized. So maybe it has the same flavor of the previous interpretation of PCA, finding a lower dimensional space on which you have the largest variance, but it's different. And actually, the interpretation is different, but the end result is the same. If I'm writing exactly what is the problem here, then the distance between AI and the line spanned by X is just given by this formula, of course, with the square. And it's a really simple exercise to show that it's exactly like PCA. The end result is just looking at the maximum eigenvector of the matrix A transpose A. But it does allow us to look at other formulations of PCA or other variants of PCA. For example, if I would like to look at robust versions of PCA, meaning that if I want a PCA that is insensitive to outliers, then we all know that it's better to look at the sum of the distances and not at the sum of the square distances. So what we can do if we want to look at a robust version is to take this problem and replace the square by nothing, by 1. And this is like a robust version of PCA. And this is, of course, different from PCA and should be insensitive to outliers. Now let's look what this problem can be, another way to write this problem. So of course, if you open this L2 norm, you get this expression. And then if you look at the objective function, then you can see that it's a concave objective function. which means that again, since it's a minimization of a concave function, you can replace the equality constraint by an inequality constraint. And again, we get actually the same model of f of ax minus gx. F here will be slightly different than what is written here. Because there is a small problem, this objective function is not smooth over the domain. Actually, it was not one of our assumptions, but it will cause some problems later on. Actually, I will give you a better reason later on why it is important to smooth the objective function. So I'm actually adding I'm like an engineer, I'm adding an epsilon square here, sorry. I'm adding an epsilon square here. And so it fits the model when I'm taking f to be this function, this sum, and g to be, again, the indicator of the L2 unit ball. F is strongly convex, by the way. It's a kind of a variation of the ball pen function. And also we have the inclusion that needs to be assumed that the domain of G, the L2 unit ball, is contained in the domain of F composition A. Okay, so these were the three examples. In all these examples, in the two options for F, they are always strongly convex. Here, everything, of course, is convex. And here, the domains are always compact. So I hope that at this point, you are fully motivated to understand why I'm looking at max of f of ax minus gx. But the results will be more general than the three examples. They will just look at this model. And again, I'm sorry to sound like a broken record. F is strongly convex, proper closed. G is proper closed convex and has a compact domain. So of course, first of all, we need to note that it's a DC optimization problem. DC meaning a difference of convex function optimization problem. There is a vast literature on this topic. Just here, I'm referring you to one of the reviews on the subject of Horst and Thoy. And let's see what we can what can we learn from the literature about DC problems. So this is a general DC problem. And yes, I know that usually when you write a DC problem, you write it as a minimization problem. But of course, it doesn't matter because it's still a DC problem when you look at minus of the objective function. So here, S and T are extended real valued convex function, and the domain of T is contained in the domain of S. And this is actually important. Otherwise, by the way, the maximum will be just infinity. Okay, so when you look at what is an optimality condition for a DC problem, I guess that the most fundamental optimality condition is what we call criticality, which says that if X is optimal, then the subdifferential sets of S and T at X bar have a joint member. So there is a subgradient that belongs both to that is also a subgradient of S and subgradient of T. So this is like criticality. And some things that we need to note here. First of all, when you look at the proof of criticality, which is actually very, very simple, it's like in 2-3 lines, you can replace this non-empty intersection property by just saying that the subdifferential set of S is contained in the subdifferential set of T. So the same proof shows that actually this, and of course, the fact that these sets are, the intersection is non-empty, it follows from this inclusion. Second of all is that for me, actually, criticality doesn't have a lot of intuition because the geometric intuition for a necessary optimality condition is to say, for maximization problems, is to say that there are no feasible ascent directions. So the literature is a bit not really consistent in the terminology of optimality condition, but at least in this lecture, stationarity means lack of feasible ascent directions. So I differentiate between criticality and stationarity. And again, other papers say different things than what I'm saying here. In general, criticality is weaker than stationarity. So stationarity implies criticality. There are a lot of results in this work of Peng, and I think that there are 2 more authors from 2017 about various options for optimality conditions. Okay, so just one example, I think that it's almost a classical example of why stationarity is better than criticality. And again, here I'm looking at maximization problems. Let's look at the function 2 absolute value of y minus half y squared. Then it has 3 critical points, just -2, 0, and 2. And among them, when you look at the stationarity points, only -2 and 2 are stationary points. And actually, really, it's a good thing that to have a stationary point, because 0 is really very far from being something that is a maximizer of the function. If it's something, then it's a local minimum. And it has feasible ascent directions. You can go either in this direction or in this direction. You get a higher value of the objective function. So this is one example, but there are, of course, multidimensional examples. So this is what I learned from DC optimization problem. So if we have our problem, which is an instance, maybe a general instance of the DC problem, maximization of f of ax minus gx, then criticality here means that the subdifferential sets of f composition A and G are not disjoint. So this is the criticality. And actually, when we look at the difference between criticality and stationarity, specifically for the 3 PCA models that I showed you before, in these models, f is continuously differentiable over the domain of G. And you can show that there, for example, criticality and stationarity is more or less the same. So that means that, at least from this point of view, it's not such a problem to get critical point because they are equivalent to stationary, again, in the 3 models that I just showed you. But the question is, can we do better? So actually, my question is, can we do better than criticality? And again, stationarity doesn't help us here. And of course, if I ask this question, it means that the answer is yes. And we do it for duality. So the first part, by the way, of the lecture will be about optimality conditions, and then we'll get to also to the algorithms. So how do we do it? We do it with what is called the Toland duality, because it's a non-convex problem. And if you look at Lagrange duality, then you won't have strong duality, and the dual problem is just a bound. So, but with Toland duality, which is not exactly duality, it's a nice B conjugate trick, you can get something which has some meaning. So what we do is the following. Since f is specifically also proper closed and convex, then f is equal to its B conjugate. So we can say that f of ax is equal to f of fb conjugate at ax. And then you can write that it's, of course, the formula for the Moreau conjugate, and you get that it's the maximum of y of axy minus f star y. Next, we plug this expression inside P, this expression of f of ax inside P, and we get a different formulation, equivalent formulation of P as a double maximization problem in y and x. Next, of course, when we see double maximization, the first thing that we do is to switch the order of the maximization. So the outer maximization with respect to y and the inner maximization with respect to x. And finally, of course, when you see something like that, then the next thing that we should do is to maximize with respect to x and use again the formula for the Moreau conjugate, and we obtain what is called the Toland dual problem. We studied this kind of duality in 2 papers from 78 and 79. And this is how the problem looks like. And even though the original problem is non-convex, this kind of duality is also, we always have like strong duality here. So the value of P is equal to value of D. We can ask the question, of course, what is the connection between the global optimal solutions or between points satisfying optimality conditions, but we'll talk about it later on. Of course, there is no, free meal here, because actually this is also a non-convex problem. So the original problem is difficult, and this also the dual problem is difficult, but maybe the dual problem is not that useless as it might look. And I hope that I will be able to convince you that it's not useless. So it's a DC problem, also non-convex. But because of the properties that we have on F and G, we can also say some properties on the conjugate of F and conjugate of G. Since F was strongly convex, then F star is C11, meaning that it's continuously differentiable and the gradient is Lipschitz. And also you can, if the strong convexity parameter of F is sigma, then the Lipschitz, the smoothness parameter of F star, it will be 1 over sigma. Since G was with the compact domain, then G star is real valued. So we have the difference, and this is actually important.
So Amir, we have a question.
Yes.
So can you read it, or yeah, otherwise I can ask.
I can look at it.
Yeah.
Okay. Decreases the measure of the data set in such a... Well, I don't understand the question. How does this model increases the accuracy of what? And which model?
No, yeah. No, that's probably the meaning of the question is that, so since you go to a dual space, you change the dimension of the problem. Yeah?
No, okay, but the final objective is to solve the primal problem. So the question is, how can we solve the primal problem in the best way we can do? The best way we can. So first of all, I want to show that somehow using the duality, I can get to better optimality conditions. And the second thing will be to show how we can find like very scalable algorithms. So the dual problem is just a tool. It's not the end result.
Good.
Okay.
Yep.
Thank you. Okay, just a minute. Okay, so let's look at the dual problem for the 3 PCA models. The first one was the maximization. I'm very consistent. I'm always missing a half here. So the maximization of half of L2 squared norm FAX, this is just PCA. The dual looks like this. Okay, again, it's difference of convex functions. And they are both, by the way, real valued. And this function, this was like the F star, is continuously differentiable. When you look at sparse PCA, which is the maximum of the exactly the same term over the convex hull of the intersection of the L2 ball and the L0 ball, then the dual problem looks like this. TS is the hard thresholding operator, that S is an integer number, and it keeps the S values components with the largest magnitude and plugs zeros elsewhere. So this is the dual problem, very different than the primal problem, I think. And when you look at the square root PCA, the robust PCA model, this was the primal problem. And when we look at the dual problem, this is the dual problem. Note that again, this is F here, and F is continuously differentiable here, because the function square root of x squared plus 1 is continuously differentiable. So these are the 3 examples, and the question again is, how can we utilize somehow these dual problems? Okay, so first of all, let's look at the primal dual relations. First of all, what is the primal dual global optimality relation? And this is not a deep result. It just comes from the derivation of the Toland dual from the primal. So for example, if you have an optimal solution for D, then any vector which is a subgradient of G star at A transpose Y, and again, it just comes from the derivation, is an optimal solution for P, and vice versa. If X is optimal for P, then every subgradient of F at AX is optimal for D. But this is nice, but it doesn't really help us too much because both P and D are difficult problems. So we don't have a lot of hope that we actually get the optimal solution. So what is maybe more interesting is to look at optimality condition. So let's say that Y is a critical point of the dual problem. So if we want maybe a point that satisfies the optimality conditions for the primal problem, then the most natural thing to say is the same like what was written here. So say, let's look at points which are in subgradients of G star at A transpose Y. But actually, this is not enough. Such points are not always critical points for P. It's more complicated. If we have an additional condition that the gradient of F star at Y bar is equal to AX, then yes, X star is a critical for P. So this is not a very good result. A better result is if we actually find a stationary point of D. And by the way, in all the examples I showed you, stationarity and criticality is very different. So if Y is stationary point of D, then yes, it's enough. It's like the relation that we had at the beginning. Any point in the subgradient of, which is a subgradient of G star at A transpose Y is critical for P. So this means that maybe we need to define a new optimality condition and we'll call it dual stationarity. So X is a dual stationary point of P if it belongs to the subdifferential set of G star at A transpose Y for some stationary point of Y of D. And again, it has to be a stationary point and not critical because criticality gives us some problems. And the result here about the relations between the optimality conditions is that dual stationarity is better than criticality. So optimality implies, of course, dual stationarity, and dual stationarity implies criticality. So for example, let's look at this problem. It's a maximization of half of x1 here. I didn't forget the half of x1 plus x2 squared over the L infinity 1 ball. So critical or stationary points in this case are actually the same. It's very much like the three PCA examples, this problem. So it doesn't matter in the primal space if we look at critical or stationary points. And this is all the critical points. So we have -1, -1, which are actually the optimal solutions. And, sorry, -1, -1, and 1, 1. Both of them are, of course, here the optimal solutions. But we also have this line segment of all the vectors that sum up to 1 and with components which are bounded by 1 in the absolute value. And when you look at dual stationary points, then only these 2 points are the dual stationary points, which are also a global optimal solutions. But in criticality is a much worse condition, at least in this case, because you have like a full continuum of points which are critical points and are actually very, very far from being the global maximum. Actually, the value that they get is 0, which is not so good in this case. So far, we used Toland duality to show improve the duality conditions. And the next thing that we'll do, we'll talk about algorithms. So we want to devise duality-based methods, but again, it's maybe a bit confusing. It's not duality in the meaning of Lagrange duality. Duality-based method that first of all converge in some sense, and usually in some sense meaning that it's a subsequence convergence to dual stationary points and not just to critical points. And second of all, methods that are able to tackle large-scale instances of the problem. So, of course, in data science, we really like to look at very large matrices, and we want something that is able to cope with these sizes. So let's go back a few years before to an instance of a scalable method, but specifically for the standard PCA problem. So there is a well-known method called OWOS method. I assume that I pronounce it incorrectly. It's a variant of the stochastic projected gradient method. Actually, if you look what is a stochastic projected gradient method, this is how it looks. And what the method does is the following. We have a certain vector, iterate xk, and then the method goes towards the direction of one of the rows of A, of one of the AIKs. It's actually like looking at a subgradient of one of the expressions in the sum that define the objective function, with some kind of a step size. I'm not getting into the details. And then, of course, the next point will be a normalization of this gradient step or subgradient step. There are a lot of other variants and more results on this kind of methods. And actually, this is like what we really want. What we want is a method that at each iteration only deals with a single row of the matrix A. And this is kind of a nice method for large problem because it's very simple and cheap. And we'll see that when we use Toland duality, we get this kind of methods. They are actually, we look very similar to OWOS method, but at the same time also very different. Okay, so let's go back to the dual problem. This is the dual problem, maximization of the dual objective function, which is G star of A transpose Y minus F star Y. And again, I'm reminding you that G star is real valued. This was because we assumed that G has a compact domain. And F was strongly convex, so F star is C11 function. So we have a problem. Okay, now I was really okay until now with dealing with maximization problems, but at the end, when we want to look at results, and I'm always switching to minimization problems. So let's look at the equivalent minimization problem when it's minimum of F star minus J star of A transpose Y. So, I guess that I could have stayed with the max, but at a certain point, it's just too much, the temptation to go to minimization problem. So what we can do, of course, when we look at dual problems, and this is something that is very common in optimization, to look at dual problems and employ some kind of decomposition method on the dual problem, something like coordinate descent. So let's employ a randomized coordinate descent on the dual problem. Now, what is a randomized coordinate descent? It's a very simple method. Here it's written for a general function f. This is the input f. T0 is the initial point, and r is a scalar, which can actually be infinity, a positive scalar. At each iteration, what we do, we pick an index, ik at random. Let's assume that it's uniform. All the analysis can be done also for any positive distribution. And let's compute the argmin of f, but only with respect to the index ik, so with respect to tik, actually. But we also are willing, it's not necessary, but we can also bound the search interval to be between minus r and r. Of course, if we plug r to be equal infinity, then it's just the full minimization. But sometimes it's good that we allow ourselves to look at the bounded compact domain. And then after we find the minimization, then we make the update, and the update is that we update the ik index to be alpha, to be the argmin that we found, and all the other indices remain the same. So this is actually, yes, randomized coordinate descent method. At each iteration, we pick a random index, we minimize with respect to this index, and move on. The only thing that is different here is that we allow the minimization to be bounded over some kind of an interval. And also not necessary. And again, we do it in the dual. So in order to, we want to know to which kind of points randomized coordinate descent method converge, then for that, I had a result with Nadav Halak, which says the following. Let's say that F is the difference of F1 and F2. F1 is differentiable and convex. This is exactly the assumption that we have here. And F2 is convex and real valued. Okay, both functions are real valued. Let's say that yk is generated by RCD, and I wrote y because we are going to employ it in the dual space. Then almost truly all accumulation points of the sequence are stationary points of the problem. So somehow, even though it's a difference of convex, a DC problem, which usually it means that most algorithms converge to critical points and not to stationary points, here, the fact that we use randomized coordinate descent method ensures us, no, not ensure, almost ensures us that we get stationary points as accumulation points. So what is the dual RCD method for solving this problem, maximization of f or ax minus gx? First of all, we need to understand, and this is maybe a continuation of the question that you asked me before, we need to, it's a dual-based method, but I want to know what is the primal sequence. So it's very natural that primal sequence will be some points, and it's an arbitrary choice of vectors that are in the subdifferential set of G star at A transpose YK. This was just the primal dual relations. So in YK is the dual sequence that is constructed by the randomized coordinate descent method. And we also make a notation that ZK is equal to A transpose YK. So this is how the algorithm looks. It maybe looks scary, but it's not. Let's say that we start with the Y00 and Z00. The general step again is to pick a random index uniformly, again, just for simplicity. We compute a one-dimensional minimizer of this function. So, but it's a one-dimensional minimization, again, over an interval, maybe. If we choose R to be equal to infinity, then it's complete minimization. And then we update Y and Z. And again, Z is just a notation of A transpose YK. And it's important to keep this Z because otherwise we'll need to make multiplication of A transpose by Y. And I want it to be as simple and cheap as OWOS method, meaning that the only thing that I'm going to do in this method, and you can see it, for example, in the way we update Z, is just to take the previous vector and add the scalar times one of the rows. So it's still a method that picks one of the rows and performs some kind of operation on this row. What is the output? So this is iterated, A, B, and C. The output is just to take a subgradient of G star at ZK plus 1. And actually, in two of our examples, G was the indicator of the L2 norm. So G star is actually the L2 norm. And the subgradient, unless the vector is 0, is just normalization. So in the examples, again, that G was the indicator of the L2 norm, at the end is that we perform normalization. So this is, just a minute. Sorry. This is very similar to OWOS method, but it's not exactly. And these small changes are everything here. OWOS method performs normalization at each iteration. So OWOS method adds a constant times A and then performs normalization. So because OWOS method is actually a primal method. So it's a primal feasible method. Our method is actually a dual method. So these Y's are in the dual space, and also Z are not exactly, and they're almost in the primal set, but not exactly. So we perform this iterates again and again, but we don't do normalization. The normalization comes at the end. This is the first difference. Of course, the second difference is the way we choose SK. The SK is some kind of a minimizer of a one-dimensional problem. So even though you can have like very different choices of F and G, always the method looks like ZK plus 1 is equal to ZK plus SKA IK. The only difference is the way you choose the step size, which is kind of strange. In most methods that you can think of, the step size maybe changes the, I don't know, the rate of convergence or something else, but no, here it really changes the kind of problems that you solve. Okay, so this is a dual RCD method. Let's see what we can prove on the convergence. And what I'm interested in is the primal convergence, because the dual convergence is also is a non-result. This was the result with Nadav Halak. So let's say, what is the theorem? The theorem says the following: let YK be generated by the RCD method, employed on the minus of the dual objective function, because I look at minimization problems. Let's assume that minus Q has bounded level sets. This is an assumption that we put sometimes. And let's define the primal sequence as always. then almost truly all accumulation points of xk are dual stationary points of P. Now, first of all, we need to look at this assumption that minus q has bounded level sets. It is required, by the way, for the problem for the method to be well defined, because if you look at the method, we perform here minimization, and in the case, for example, when r is equal to infinity, maybe the minimization is not attained, and when you have this bounded level set, then the method is well defined. But the problem with this kind of an assumption is that it's not always easy to verify, to say bounded level set. It's very not exact. So the next theoretical question was, can we replace this bounded level set assumption by another property? So here it's very natural to look at the asymptotic function. And just reminding you that the asymptotic function of a function h is this lim inf. And what is important for me is the basic result of asymptotic function is that if the asymptotic function is always positive for any direction, then it has bounded level sets. So maybe we can write a different condition than bounded level sets. So let's write a condition that says that the asymptotic function of minus q, which is actually this term, is always positive. But I just replaced one unverifiable condition with another unverifiable condition, because what is the asymptotic function of a difference of two convex functions? There is actually I don't think there is a general calculus for the asymptotic function of the difference of functions, but we did find a calculus rule, but it has some assumptions. So if u and v are real valued, such that v, this is the function that we subtract, is Lipschitz continuous and convex, then we have this, yes, the asymptotic function of the difference is the difference of the asymptotic functions. Luckily for us, it is correct here actually that in our example, in the case where V is G star of A transpose, it is Lipschitz. So yes, we can replace the bounded level assumption by this assumption, which is kind of explicit. And in all three PCA examples, it is satisfied. So for example, in PCA and sparse PCA, these were these examples. Here it's trivial because F star is half L, I didn't forget the half L2 squared norm of Y. Then the asymptotic function of the conjugate is just infinity. So of course it's positive. It's more complicated for the square root PCA, where this was the F star Y was this function. Here, the asymptotic function of this function is this function. So we replace the square root of I squared plus 1 by the absolute value, actually by the square root of di squared. So it's absolute value of di. And then to check whether this condition is satisfied, then we need to verify that this condition is satisfied. And actually it is, it's not difficult, it's just the Cauchy-Schwarz inequality. And if we didn't have the epsilon, then it would be a problem. Then it would not be satisfied, and actually the entire method will not be defined. So I added, this is the real reason why I added this epsilon square, because it doesn't work, otherwise it doesn't work, this approach. And
we have a question, Amir, on the
yes.
previous lemma. So do you need global Lipschitz or local Lipschitz?
Here we proved it on global Lipschitz. Okay. Maybe you can prove it also on local Lipschitz, but the way we did it, it was Lipschitz. Yes, okay.
Good.
But maybe it is also correct then. Okay, the next question is whether we can show some kind of a convergence right now. Of course, the problem is non-convex. So you cannot prove convergence to the global optimal solution. So, but what we do want to show is convergence of some kind of an optimality measure, at least of the dual problem. We were able to do it only in the case where G is the indicator of the L2 unit ball. So the problem P, F of AX minus GX, reduces to maximization of F of AX over the L2 unit ball. And the Toland dual problem is the following problem. And we have an additional assumption that is satisfied, and it's actually not a real problem. We assume that the argmin of fx is just 0. It was on in all of our examples. And we want to show some kind of a rate of convergence. The problem is that in general, this objective function, this Q, is neither convex nor smooth. So what is an optimality condition, optimality measure? If the objective function, for example, is just, if we look at, for example, unconstrained smooth optimization, then optimality measure will just to look at the gradient of norm of the gradient of the objective function, and then you can ask question of what is the rate of convergence in which the norm of the gradient converges to 0. Luckily here we can show that if the initial point of the dual RCD method is 0, which actually this was how I defined it, then the dual objective function is always differentiable, both at yk and actually also in all accumulation points. So yes, here it's very simple to understand what is the optimality measure. It's just the norm of the gradient of the dual function. Again, the difficulty here is that in general, looking at something like L2 norm of A transpose Y is not something that is differentiable, but we don't have this problem. So we can show a 1 over n, or maybe it's 1 over square root of n if we look just look at the norm of the gradient, but it's a 1 over n rate of convergence of the expectation of the norm of the gradient of the dual function. Sorry, that was a very long sentence. I will not get into the details, of course. Let's look at how the dual RCD method looks for the different PCA models. So let's start with the standard PCA. So this was the objective function. This is the dual function. What we need to do, the main actually task here is to perform the 1D minimization problem. So how does this 1D minimization problem looks like? It looks like this 1D problem. And it's very simple to show that, although the details are very detailed. We can show that it can be reduced to finding roots of a quartic polynomial. So if you are brave enough, then you can actually write an expression for the roots of the polynomial. You have explicit expressions, but I didn't write it because it's not very interesting. And then you get the usual method. So we pick an index of, and then we solve this 1D minimization problem by solving quartic polynomials. And then we make the update. And again, the update is to take y or z and add some kind of a constant, again, depends on these quartic equations, times the AIK. So this is for PCA. Again, I'm not writing exactly what is the quartic problem. If you look at the square root PCA, the robust version, so this was the primal problem. This is the dual problem. Actually, it's more or less the same. The only difference is that we need to solve different one-dimensional minimization problems. And this is the minimization problem that I'm solving. It's not, it looks complicated, but it's not. The nice thing is that also here we get quartic polynomial equations, but it's not a problem. It's just, but they're different than, of course, the quartic polynomials that we had before. So I didn't write like a slide with like 15 expressions for how the roots look like. And this is actually exactly the same like in the previous slide, but the difference is, of course, that we solve different quartic polynomials. So this is part of the point that I talked about before. The only difference between the different dual RCD methods are the way we choose the step size. And this is what makes all the difference. Now, what is interesting, and maybe gives you some thought for the future, is what happens with the sparse PCA problem, because then the 1D minimization problems are not that easy. So let's look at the sparse PCA problem. This was the primal problem. The dual was this one. I remind you that TS is the hard thresholding operator. We perform this 1D minimization problem, but if you think of it, if you think that TS is the hard thresholding operator, it's not that simple. It has a lot of branches, this 1D minimization problem. Sorry. But of course, we have the same type of update formula. It doesn't change. but we don't have an explicit formula, or it's not that important that it's explicit. We don't have like an efficient method to solve the 1D problem. But here we do have some hope, not like with the COVID. Then the hope is that there is some structure in the problem. So the kind of one-dimensional problems that we solve are these kind of problems, half t square minus, again, half thresholding of a certain fixed vector v plus tw. We can show that, first of all optimal solutions are bounded in some kind of an interval between minus L2 norm of W and norm of W. And actually this bound is, when you look at numerical examples, is very tight. So these are actually examples, realizations of these one-dimensional problems. The red, the interval that is marked by red is this interval between minus L2 and plus L2 norm of W. And you can see actually that the optimal solution, the minimizer, is in all of these examples is very close to the bound, to the one of the endpoints of this interval. So it's not like a huge interval where that the optimal solution is inside. But in any case, this is the theoretical result. And the second result is that we can show that these one-dimensional functions are Lipschitz continuous, and we can measure this Lipschitz continuity. It's equal to 2 times L2 norm of W. And this means that there is some hope, even though the functions are, they are quite general. There are Lipschitz continuous functions on a given, and we can make the minimization on a given compact domain. There are some effective methods to solve such problems in a global optimization. And in any case, by the way, when practically, if you use any unimodal optimizer, like in 99.999%, you get really the optimal solution, but it's not a theoretical result. So summary, the main points are the following. We looked at this primal problem, maximization of f of ax minus gx, and the dual problem, which is also a maximization problem. Both problems were DC optimization problems. We looked at the optimality condition, which was called dual stationarity. It's stronger than criticality. We looked at dual randomized coordinate, descent algorithms. We know that they converge almost truly to dual stationary points, and they are very scalable and only use one of the rows of A at each iteration. And we just need to solve a one-dimensional problem at each iteration. So thank you.
So thank you very much, Amir, for the very nice talk. So it is time for questions. Just write your questions in the chat, or unmute your microphones. So then, So then I will ask 2 questions, Amir. So okay. I mean, you assume for the problem P that the convex part is strongly convex, but probably you don't need this, since you can assume convexity of both parts and then make it strongly convex by adding and subtracting the same quadratic term, let's say.
Okay, so what you suggest is to add the same like epsilon times L2 norm of x square. And then look at the dual problem.
And then subtract it, add it, subtract it, and put 1 to F and 1 to G. Yeah.
Yes.
And then, probably there will be some modifications in the dual and so on, but
that's exactly the point. That will make the that will make the dual, all the analysis with the conjugate much more complicated. So it's not even evident that we can, even in the special case of the PCA models, that we can compute that explicitly. I'm not sure. I know, I mean, this is a well-known trick that you can always do that.
No, you can do that, I know, but I'm not sure what is the effect on the...
No, so this is a question, but then you can look at even more general problems then, and then,
I think that in the 3 examples that we showed, it's not a problem to compute the conjugate in this case of the sum of the functions, and that's a good idea.
Yeah. Second question. So, I mean, so what I understand is that it's important to use the algorithm you used, since this algorithm, generates a sequence which converges to this better notion of stationarity. So are you aware of other methods which provide you this kind of better stationary solutions?
No, for what I know, this is the first algorithm that does that, but you know, maybe I'm missing something.
Okay, no, but this is important aspect. Yes, then you very
yes, I think also some people will think that the aspect that it's a very cheap algorithm is even more important. But I think that yes, it's also important that it converges to better optimality conditions.
Okay, thank you. We have another question. Vei Li, would you like to unmute your microphone, or you can just read the question?
No, okay, so the question is, can I explain better about the TS operator? Does it computationally friendly? There's no, it's not a, no, it's okay. TS is just the R thresholding operator. It's trivial to compute. It's a linear, it's O of n operations. You just take the S elements with the largest absolute value, you keep them, and then you plug 0 everywhere else. So that's not a problem. The issue for example, in the last problem is that when it's a part of a one-dimensional minimization problem here, then maybe it becomes a problem, but just computing TS is not an issue.
Okay, thank you. Manuel Bomse.
What is the relation of local optimality to dual stationarity? That's a good question, Manuel. Actually, the only thing that we know that usually this kind of we only show that if point is the global maximum, then it's a dual stationary point. We didn't show, but we actually didn't ask the question, what happens if a point is a local maximum point, whether or not it is a dual stationary point? That's a good question, but we need to look at it. I'm not sure what is the answer.
Okay, thank you, Manuel. So, other questions, comment?
Thank you.
Yeah, then let us stop here, Amir.
Okay.
Thank you for a very nice talk. So,
thank you.
I want to thank the audience, the colleagues for attending the talk. So a lot of participants at the beginning of the second season. So thank you very much for coming. Thank you very much to Amir. Thank you, Amir, very much for a great talk. It's a very nice starting of the second season. And so we will post the video of the talk and then the slides on the website of the seminar. And I would just like to announce that the next speaker will be Zhongxi Pang. And yeah, we already got some confirmations of the colleagues who we invited to talk. So we are looking forward to a very nice second season. Thank you, Amir. All the best. Thank you to the participants, and see you next Monday.
Bye-bye. Thank you.
Thank you.
Bye.
Bye-bye.
Thank you.